Welcome to the Micromodules series, Understanding Bias in Epidemiological Studies. In this series, we will introduce the concepts of common biases in epidemiological studies, why these biases can distort the research findings, and how to address these biases. In this first module, we will introduce the general concept of bias, explain why bias is bad for epidemiological studies, and introduce the three categories of bias. Before we dive into biases, let's start with a basic but important question. What are the objectives of epidemiological studies? Epidemiological studies typically serve two purposes. The first one is to measure the frequency of a health-related factor and event in a defined population within a given time frame. For example, the prevalence of smoking or the 10-year incidence of lung cancer. The second one is to evaluate whether and to what extent health-related factors and events are associated with each other. For example, the association between smoking and lung cancer, which can be measured as risk ratio, odds ratio, and so on. These results, whether they are prevalence, incidence, risk ratios, or odds ratios, are all numerical values. However, there's always a difference between the observed value and the true value. This difference is what we call error. There are two types of error. The first one is random error, which is caused by chance. Most epidemiological studies are sampling studies based on samples rather than the whole population. That means the studies are conducted in a proportion or a subgroup of the target population. So, the sample size may range from very small, such as only a few individuals, to very large, such as millions of individuals. As every individual is born different, the results are bound to vary across samples, simply due to chance. For example, the average blood pressure can vary significantly across different populations. Furthermore, the numerical values of many parameters within an individual, such as blood pressure, blood sugar, and body weight, are naturally and randomly fluctuating over time. Thus, the result from a small sample or from a single measurement may not reflect what is really going on at large. The difference between the two is called random error. Random error can be reduced by increasing number of total individuals and measurements of each individual. For example, increase the sample size from 50 to 500 individuals and use the average blood pressure of multiple measurements rather than that from a single measurement to represent the blood pressure of an individual. The other type of error is systematic error, which is also called bias. Bias is caused by problems of study design, participant recruitment, data collection methods, or data analysis strategies. For example, if a cross-sectional survey that aims to investigate the smoking rate in general Hong Kong adults only recruits adults with high socioeconomic status, who are less likely to be smokers. In the survey, the smoking rate could be underestimated, and this underestimation can be referred to as bias. Bias can be prevented or reduced by improving the study methodology, such as adopting the most suitable study design for answering the research question, using appropriate sampling procedures, good quality control of data collection, and so on, which we will explore more throughout this micromodule series. When conducting epidemiological studies, we always want to avoid or reduce bias, because it can lead to distorted results and potentially incorrect conclusion, such as overestimating or underestimating the true frequency or strength of association. Sometimes it can even reverse the direction of the association of interest, for example, suggesting protective effect of a harmful exposure. Also, unlike random error, which can be reduced by increasing sample size, the effect of bias cannot be reduced by increasing the number of participants. For example, using an uncalibrated blood pressure monitor that reads 5 millimeters of mercury higher than true values will always overestimate the blood pressure, no matter measuring 100 participants or 10,000 participants. There are three broad categories of bias commonly seen in epidemiological studies, which are selection bias, information bias, and confounding bias. Selection bias is caused by systematic differences in characteristics between the study sample and the target population to which the study findings will be generalized. This type of bias may occur at three stages, including participants' recruitment, participation, and retention. During the recruitment, selection bias may occur if the individual selected to participate in the study differs systematically from those who are not selected. At the participation stage, selection bias may occur if the individuals who agree to participate in the study differ systematically from those who choose not to participate. At the retention stage, selection bias happens when participants who stay in the study differ systematically from those who drop out. Information bias occurs when the information collected or measured in a study is inaccurate, when an inaccurate equipment is used to measure blood pressure, or participants fail to accurately report the number of cigarettes they smoke per day. This type of bias is also known as measurement bias or misclassification. There are two types of misclassification, namely non-differential misclassification and differential misclassification. Non-differential misclassification means the degree of misclassification is comparable in the study and comparison groups. For example, using an uncalibrated blood pressure monitor, the blood pressure readings of all subjects in both groups are 5 millimeters of mercury higher than the true values. Differential misclassification means the degree of misclassification is not comparable in the study and comparison groups. For example, in a case control study where the investigators conduct more in-depth interview in the group with cancer to obtain their past history of smoking than in the group without cancer, hence less misclassification of exposure level in the cases group. Confounding bias occurs when the observed effect of exposure on the outcome as measured by odds ratio, risk ratio, and so on is not purely the effect of exposure per se, but a mixture of the effects of exposure and other factors. These other factors are called confounders. Here is a hypothetical example. Researchers followed 2,181 smokers and 3,327 non-smokers over time to investigate the association between smoking and lung cancer. Surprisingly, they found 1.4% of smokers and 3.5% of non-smokers developed lung cancer during follow-up, respectively. At first glance, this seems to suggest that non-smoking would result in higher risk of lung cancer, which contradicts our common sense. A closer look at the data shows that the age composition differs between smokers and non-smokers. More than half of the non-smokers are old people, while only 7.6% of the smokers are elderly. As older people are in general at higher risk of lung cancer, the observed higher risk of lung cancer in non-smokers could be partly or totally due to the older age in this group. This phenomenon is called confounding. Okay. In this module, we introduced three broad categories of bias, namely selection bias, information bias, and confounding bias. All of them could lead to distorted results and incorrect conclusions. In the following modules, we'll elaborate on the mechanism and common forms of each bias and the methods for addressing these biases. Thank you for listening.